Does it work?
I think I'll just press. There you go. So thank you again for giving me the opportunity to give a longer talk this time. I'm going to talk about a project I have called RandomNets, which is vectorized ensemble neural networks. So often in QSAR applications and some of the models we actually regularly use, like random forest, are enhancing their model performance by ensembling. You can have a weak model like decision trees, but if you put them together in a forest of trees and averaging the prediction, and you make sure that all of the decision trees are slightly different, then you get suddenly a quite strong predictor model. There are various ways to ensure that they're different. One of them is bagging, bootstrap aggregation. We resample the data set with replacement. So sometimes a sample comes into the new data sets more than one time, and sometimes the sample doesn't come in at all. And then we build fastly built decision trees based on these data sets and join them together in the forest. Another way is the random subspace methods. We could call that feature bagging, where we present a subset of the features to each decision tree. That is nice if we have redundant features or correlated features that are not saying completely the same thing, but they are not completely orthogonal. Then each decision tree will get a little bit different decision, and the ensemble will become stronger. And it seems to be an efficient approach. In a lot of these blind challenges, as example in the TOX 25 blind challenge, all of the top contenders on the leaderboard seem to be ensemble models or a consensus model combining different model types for the final predictions. I like neural networks, and often ensembles there, you approach it, you loop over your data sets, and you loop several times during training, and you train a lot. And then in inference, you again loop over your different models, and you have a lot of managing to do by saving and loading all these models and handling them. And also the efforts suddenly scale linearly with the number of models. If you want 25 members in your ensemble, it takes 25 times longer to train it unless you have 25 machines to train it on. So there's often a need to have some sort of framework if it doesn't exist already. But of course, it's maximum flexibility. You are completely in control of everything that goes into the ensemble. But another trick is actually to avoid for loops by using vectorization. If we can instead vectorize our problem and use some array library like NumPy or PyTorch, suddenly we avoid that, and we can get blindingly fast computation because Python calls these efficient libraries in the backend. So maybe we could also do that, simply add a new dimension to all the tensors that we will then put through our neural networks. We can add the dimension, and we can expand here example by the input fingerprints mini batch, and suddenly we get something that have 3 dimensions, where the last dimension is the ensemble dimension. And then of course you need to adapt the rest of the neural network architecture to take in this, but suddenly all our parallelism is handled on the GPU, and then we could expect it to work better. Then comes the question, now we have a kind of monolithic neural network structure, so how do we actually induce the differences between the thing? And similar to random forest, and maybe also similar to this old fable about the blind man and the elephant, quite old, they all see a different truth. They're blind, they cannot see the elephant, but they touch it. One touches the leg and say, oh, it's like a column, and another touches the trunk and says it's snake-like. And there are different versions of this, and some of them, they start to talk to each other. They discover that their truth doesn't rule out another person's truth, and maybe the truth is actually something you can discover together by talking about it, a higher truth. And in other versions, they start to argue who's lying and start fighting. So we hope it's the first thing we can do with our networks. So Input masking was actually quite easy to implement by this. We make a PyTorch binary mask that we add on the input. But getting the samples to only be presented for certain members of the vectorized ensemble was a lot more difficult. But in the end, it seems to work. So one thing I discovered quite fastly was that I ran out of video RAM on my GPU. So I couldn't reach the number of ensemble I had in mind. So I was experimenting with this, and now it sounds like here on the slide that I implemented weight sharing to share the memory. I actually didn't think that I was implementing weight sharing, but suddenly the network started to work much better, and I could also have a much better memory consumption of it. It's still a fixed input mask, and we have this sample masking where we only back propagate for some predefined output neurons. Features here in this experimental setting was Morgan fingerprints radius 2, but basically any scikit-mole transformer pipeline can now be plugged into the data module for this. So if you want another fingerprint, it will also be available. And now I have no more excuses. Let's go to some of the results. How does it look when we do it like this? So the first experiment was to see how do we compare to a single neural network without masking. Do we improve our performance? And we do it quite markedly. We have the same number of training epochs, 50, and the masking is set for 0.5 here. And already one member of the ensemble where we only leave out some features is actually a bad idea. We leave out some important information for that network, and it cannot reach the same performance as a single network that sees everything. But already two members of the ensemble seem to work better, and we continue to actually improve our network up to around 25 to 50 members of the pseudo and ensemble. And we see the same with the error. The mean square error keeps dropping up to the same kind of plateau. I used a data set from Escape degree. So what about the feature masking versus the sample masking? So I did some bridge search, and feature masking around 0.7 seemed to be very good for this data set. We can see the light yellow areas around 0.7. But going to the right with more sample masking just didn't seem to do anything, or actually just be detrimental. So that seemed to be inversely proportional to the difficulty in implementation. So sometimes the simple ideas that are easy to implement also just works the best. But it was good to examine this. Then we can look at the training, because that was what we were really after. We don't want to use very long time for training. And this is where it really was nice to see that we, by only using 2 times the training time, could actually train 25 to 50 members of the ensemble, which was also where we had a plateau. So that's a very modest time investment that we need to do to actually get to a point where we have our optimal performance. And I think part of the reason is that we transfer the fingerprints and the target values to the GPU before we do the expansion. So everything from there is done very efficiently parallelized on the GPU that is built for that purpose. And I think also another thing that also happens is now we start to increase our effective mini batch size. We have a mini batch size of 64 or 128. Then we transfer to the GPU and expand along the ensemble dimension. So suddenly our mini batch size is much larger, which could maybe be a reason why we see a more robust training in fewer epochs. One data set is, of course, good to show that we do some performance improvements, but I also wanted to check if this is something that holds true for other data sets. So I used 133 regression data sets from EscapeDB, where I knew that they could build reasonable models. There I could see that for actually all of the cases, it seems to be a better idea to use the ensemble approach than using a single ones. the effects seem to be more pronounced for the smaller data sets, whereas the larger ones here, lightly colored in yellow, are closer to the unity line between the two approaches. One thing, now we use the input mask, and that reminded me of this famous dropout methods from Hinton and some other grand old men in neural networks, where you drop out output from neurons in order to prevent overfitting. So we're doing a little bit the same here. We can also drop out on the input layer and see how that performs. So the reason, the way I did it was that I had to sample the network multiple times with dropout input active, the same number as we had numbers in the ensemble, and then we actually also averaged the approach, the predictions from the dropout in version of the network. But even though I expanded the training time to 1600 epochs compared to 50 to maybe try and compensate for the larger effective mini-batch size, we could not reach the same performance as we had with the random ensemble approach. And another thing I also liked about this graph here is we seem to have a broader area of the hyperparameter for the mask fraction, which all other equal would maybe make it more easy to build a robust model and do a hyperparameter tuning. Then when I worked on it, there was this surprising effect of dropout in. Normally with a dropout layer, it's active during training. There we drop out certain outputs from neurons with a certain probability. And then during inference times, this is turned off and the output is scaled back to compensate for that now all neurons are firing, whereas before some of them were blanked. But if I turned off the dropout in layer in my network, I just saw this systematic diminishing in the prediction, which should actually have been compensated by the rescaling of the output there. So that was a bit curious. Why is this? And it is maybe because we are not really able to learn a different scaling of the input. It's fixed. So the effect of the dropout layer is not only in itself, but it's also on how it affects the settings for the previous layer in our neural networks. But if other people have other ideas how this could be and are deeply into dropout networks and how they work in PyTorch, I would appreciate it if you reach out afterwards. So, the last thing I noted was now we create this random feature mask. It turns out that sometimes certain features will be masked more than others. And that's, I thought, could maybe lead to a situation where sometimes you're lucky that you mask out features that are irrelevant and don't mask out features that are very relevant. And other times it could be the other way around. But maybe we could develop a kind of a random mask that anyway are more balanced in the amount of times the features are filtered away for the ensemble. I developed this balancing mask approach where we sample the features and distribute them. And when we don't have any more features, we refill that buffer and go to the next and the next and the next ensemble member. So in the end, we have more or less included the features the same number of time, but distributed randomly across different members of the ensemble. And what we see is that we get on average a higher correlation and a lower error and a lot less variability on how our models perform. We also see a slightly higher standard deviation on average between our ensemble members. That's also something that can improve performance a little bit. So another thing we get with ensembling that is often used in the modeling is that we can look at the standard deviation of the predictions between the ensemble members. The idea is that if they all agree, we are more certain that the prediction is reasonable. And if they all are more or less random all over the place, Maybe something is difficult with the input space. We may be in an uncertain area of the model, or we are outside the applicability domain. So here for this serotonin transporter, I examined how is the error on the test set, the absolute error, and looked at different segments. What are the 95% of the samples within this absolute error? And for below 0.3 standard deviation, we see 95% of the test sets within 1.2 units. But if we go to about 5, it rises to 1.75% of the units. So there is a slight correlation between what you could see of the expected error on the predictions. Another way to look at it could be to challenge the model. Now we know the domain here, it's a serotonin transporter. So I took a couple of famous drugs and tried to see what does the model say about this. And the model is a regression model. It says only seen active. So it says, yeah, they are all weakly active, but it has a higher standard deviation for most of the compounds. Viagra comes within 95% of the test sets, that boundary. But for Taxol, which is a big complex natural compound, it seems to be a very high standard deviation. So that also seemed to help us determine if we are outside the applicability domain. So in conclusion, we tried to vectorize the neural networks in order to make it more optimal to do training and inference. And feature masking that was easy to implement was actually the one that gave us the effect. The training is sublinear in scaling. We don't need 50 times longer training time in order to train 50 members of the ensembling. And we see this improved performance compared to single networks on a lot of different data sets, suggesting that it's, at least for these regression type tasks, are a robust approach. Compared to feature dropout, which could be a similar technique to do this, we show a little bit less sensitivity to the hyperparameter choice and also slightly better performance. So all in all, I think this is an attractive approach when we compare it to single feed-forward neural networks, and I open sourced it. And currently it's just for a regression model, but it could be easily expanded to classification and other types of tasks. Yeah, I'd like to acknowledge a lot of the open source contributors of the world. I know you are also out there in this audience, and I mean, it's an important thing that we are open about this, because this little interesting project was built on top of a lot of packages that I couldn't have done it in a timely fashion without. And also not just open source, but also people that release open molecular data sets to the world allow this type of experimental work. And I think if we had only had licensed software and proprietary data sets, we would not be where we are today with regard to what we do in cheminformatics. So thank you very much for your attention. And are there questions? Lots of questions.
Very nice. Where you see how is the algorithm on the floor?
You say you're missing a comparison with?
Well,
yes. I actually wanted to make a slide because during my training of this, what I've really shown is that it's comparable, better than single feed-forward neural networks. I've not gone into if it's better than CatBoost or Random Forest or other thing. During my training, I was doing that, what you say, I compared to a well-tuned Random Forest, and I saw, well, I approached this, but I don't pass it. And then when I made this talk, I said, okay, I'll make a hype management slide. I will show this and do this, and then you can see, okay, it's not better than that. But then with the balanced masking and maybe some of the improvements, I could actually not beat it with the Random Forest. And then I thought, okay, this may need more examination before I go and present it, because I don't want to overhype this is better. It would need more careful comparison, right? So thank you for your question. Yes.
Yes, very nice work. First of all, OJ Baking says hi. Thank you for the reference for slides.
Sorry?
OJ Baking says hi.
Yeah. Okay. Great.
It's really interesting to see, and have you also compared this in a temporal split or cluster, chemical cluster-based splitting technique?
No, I have not dived into. Yes, the question is if I have used other types of splits than random splitting, some of the more challenging like scaffolds type splitting or temporal splitting or cluster-based splitting, and the answer is no, I have not done that yet. I expect that maybe the ensemble approach would be more robust to that, but it's also really depending on your data set and your clusters, what you do there, right? So I'm a little bit cautious there if we could also see something there.
And have you checked for diversity in relation to 130 models?
No, I have not done that, but that's a good suggestion. Thanks. Yes.
I want to follow up on the temporal splits.
Yes.
Because I think it would be interesting to see, of course, in the public domain, we don't have real temporal split data, so you can't really do it. We published a paper a few years ago with simulated temporal splits that you might want to try. Sort of.
Yeah.
The SynTab paper.
Yes. I think I know it. Yes.
Set up the same as the EC.
Yeah. Should I still repeat the suggestion? Yeah. So Greg suggests that I look at if I can't get a hold on temporal split data sets, that I use these simulated temporal split data sets that he published a couple of years ago in a paper.
But I have an actual question.
Yeah, we also have a question. Okay, great.
Thank you for that prompt, for me to do self-review. So I have an actual question. If you look at anything other than Morgan fingerprints, and if you look at the size dependency, because Morgan fingerprints have a particular characteristic that they have a very low bit density, and each individual bit is not particularly informative. And so I'm curious if you look at different bit densities, which you can sometimes have very large effects on random forest just by changing the size of the fingerprint. Or if you look at other descriptors where the descriptor information is more dense.
Okay, so Greg's question is if I have looked at bit density or different fingerprint types in order to see the effect on the performance. And no, I have not, but it sounds like a very interesting approach to get deeper into what's happening. It would be easy to actually plug in different fingerprint types and set the input dimension differently.
But you're using your pipeline anyway.
Yeah.
Yeah, great question. ECFPs are by nature extremely correlated. This approach then reduce the correlation between the different bits. So the overlap will always have high correlation on the feature. If you compare this against like the atom pair of feature orientation, it's effectively less pronounced, but this would kind of mean that what the phone is doing with the 3D full correlation and helping the model to converge.
Yeah, I think this was a comment on ECFPs are naturally much correlated, right? And therefore we should maybe expect that if we see less correlation between the features as you could get with atom fingerprints, it would not be as pronounced an effect that we see by doing the ensemble. Was that correctly understood?
Yes, that's masking your rules.
I have not tried out other fingerprints, as I said to Greg just before, but it could be an interesting thing to see how sensitive it is to this other kinds. We can also expand to descriptors and other things and see if it's a general good idea or if it's just coupled to ECFPs.
Esben, can you describe the features that serotonin said, because it doesn't tell me much.
Sorry?
What were the features that serotonin says, serotonin transporter said?
What the features are?
Yes. describe it?
I have not looked into the SAR of this receptor. It's a play data set I have been using for a lot of different model types.
Regression problem, but what was the target to predict? Was it solubility? Was it
No, it's binding
Binding.
to that. Yes.
so binding? Can you say that this feature masking can generalize to other types of problems? The improvement that you observed during feature masking can generalize to other types of problems, regression problems?
No, I cannot, because it would be a good expansion to go into other types of feature problems like admit problems or things you mentioned, solubility. That would also be interesting to see if that also carries out, or is it's just related to that we mask out different fingerprint bits that are maybe highly correlated here.
Oh, I have a couple of questions.
Yes, great. Okay, sorry. Yeah. Can you speak up a little? I find it very hard to. The question is if I checked if the uncertainty is well calibrated for the ensemble, and no, I actually don't think so. It doesn't seem it, and it's not a very high correlation we see between these things. So it is a kind of indication, but I would not take it as uncertainty per se directly from the model. Yes. So thank you.